Okay, so today we'll be discussing the shortest path problem. But before we actually get started on what the shortest path problem is, we should discuss a very important thing that we need to know before that. That is, what is a graph? We briefly went over those the other day, but it's basically a set of vertices and edges, and an edge can either be weighted or unweighted, directed or undirected. In the case where an edge is undirected, we can just assume that the direction goes both ways. And these are all examples of graphs, and if we actually look at the one all the way on the right, this should look familiar to everyone. That is a binary tree, which is just a specific kind of graph. So now if we actually get into what the shortest path problem is, it's exactly what it sounds like. We are looking for the shortest path between two nodes in a graph, such that the sum of all of the edges is minimized. And we can categorize them into 4 different types. We have the single pair shortest path, single source shortest path, single destination shortest path, and all pairs shortest path. So the 2 algorithms that we're going to be talking about today will actually cover the first 2, single pair shortest path and single source shortest path. So the very first algorithm is Dijkstra's algorithm. So it was conceived by this man, Edgar Dijkstra. He's a Dutch computer scientist in 1956. And we can kind of think about him as the father of shortest path. So here's the pseudocode, but we're actually just going to walk through an example because it'll be a lot easier to see how this algorithm actually works. So given this graph where we have source node A and target node F, the problem is looking for the shortest path from A to F. So before we begin, the very first step of the algorithm is to initialize all of the distances from the source to any node in the graph to infinity. And that's because both of the algorithms that I'm going to be talking about today are based on the principle of relaxation, which is basically we just overestimate the solution as the algorithm goes on. It'll become more optimized until we hit the optimal solution. And obviously, infinity is the most over-exaggerated estimation. So before we actually start traversing through the graph, we are going to initialize the distance from the source to itself as 0, because hopefully there shouldn't be any, it shouldn't take anything. So the main thing to keep in mind is that with Dijkstra's algorithm, as we continue with the algorithm, we're going to start marking nodes as visited and unvisited. Once a node is marked as visited, we're never going to come back to it again. So right now, as we can see, they're all unvisited. So the very first node that we're going to start with is our source node. That's node A. So node A has 3 neighbors, B, D, and C. And from this node, we are going to initialize the distances to these other 3 nodes. And we can see that as being the distance from the source to A, which is 0, plus the distance from A to each of the nodes. So B gets initialized as 2, D becomes 5, and C becomes 6. And then now we're done with A, so we have marked A as visited. Now the second node that we're going to visit is actually the node that has the minimum distance from the source so far. So in this case, it's node B. So in order for us to mark node B as visited, we have to visit its one neighbor, which is F. F was not initialized, it was still at infinity. But once we hit this path, B's distance from the source is 2, and from B to F is 7, which is why F gets marked as a 9. Now the next node that we'll be looking at is node D, because the distances that we have so far are D is 5 away from the source, C is 6 away from the source, and F is 9 away from the source. So D has 2 neighbors. We have node C and node F. So in the case of node C, if we actually go from A to D to C, the distance would be 7, which is worse than what we already have, 6. So we're just going to leave that distance. In the case from going from A to D to F, that new distance actually becomes 8, as opposed to what we previously had, which was 9. So that distance is going to get updated. And we now mark D as done, and we're never coming back to D. And then the same thing will happen for node E. E will get initialized as 7 because it goes from A to C to E. And then we mark C as done. Now we're going to hit E. And then E will say, OK, my one neighbor left is F, but the distance that I have is a lot less than what's already been there. And then we have one last node, which is F. And that doesn't have any neighbors. So at the end of the algorithm, we're left with the shortest path from A to F being 8. So now this is great and all. This gives us the shortest path between two nodes. But what if we wanted the shortest path from one node to the rest of the nodes? One thing we could do is we could just modify Dijkstra's. But what fun would that be? So we're actually going to be talking about Bellman-Fords. So this guy, the man in the bottom, that's Richard Bellman, and that's Lester Ford. So this will give you the shortest path from a single source node to all of the nodes in the graph. And the important thing about this is that it can handle negative weights, which means that an edge doesn't necessarily have to be positive. Going from, let's say, edge from A to B could be negative 2. The only caveat with that is that you can't have negative cycles. So if if there's a cycle from A to B to C, I can never have a total negative sum in a closed loop. So again, this is a pseudocode. If y'all would like to look into it, I highly encourage y'all. But we're going to go through an example so it's easier to see. So with Bellman-Fords, one thing to keep in mind is that the maximum number of iterations will be v minus 1. Where v is the number of vertices. And in each iteration, we'll only be going through at maximum e times. So the very first time, we'll start with our source node. So this looks very similar to the way Dijkstra started. A is initialized to 0 while everything else is infinity because we have no idea how to get there. So starting with node A, we can initialize B and D because we know from A to B it's 7 and from A to D it's 2. Now we'll keep on going down the nodes. So from B, we know our distance from the source to B is 7 so far, and B's only neighbor is D. That'll give us a distance of 5, but as we can see, D is already initialized to 2, so the 5 doesn't really matter. Now, it gets interesting when we get to C. So C has 3 neighbors, but we actually don't know the distance from our source to C yet, so that one just stays as infinity. For D, we know that the distance from the source to D is 2, and its one neighbor is E, so then we can initialize E to be 4. And then looking at E, now we can initialize C, because the distance from the source to E is 4, and then the weight from E to C is -1, so that'll give us a distance of 3. And then F we can't get to because, well, this doesn't have neighbors. And so this is our first iteration. Our second iteration is going to be the same thing all over again, except this time, now that we have the table populated, values might start changing a little more. Looking at A, none of these distances are going to change. If we look at B, again, this distance will not be changing. If you look at C now, we can actually change B's value because that was at 7, but now if we go from A to D to E to C to B, that's actually a lot shorter. So that'll give us a distance of 6. And using C, we can also initialize F to be 6. We'll going through D won't change anything, going through E won't change anything, and going through F won't change anything. And this will be our third iteration where we go through all of the nodes. And with this algorithm, you'll actually go through until there are no more changes to the entire table. So by iteration 3, we're done. Nothing's changed in the table. So now we have the shortest distance from node A to all of the other nodes in the graph. So why does this matter? So there are a few real-life applications. One would be in biology. They actually use algorithms like this to model the spread of infectious diseases. I'm not a big bio person, so I can't get into the actual specifics of that. Another way that it's used in real life is routing protocols. So all routers in a network, this is how they would transmit like updated forwarding tables, just transmitting information in the most efficient way possible throughout an entire network. And then an example that I'm sure all of us have used, Google Maps. So we're actually not sure what the exact algorithm for finding, let's say, how do I get from full stack to taiyaki, which has great ice cream, by the way. We can pretty much be certain that it is some form of Dijkstra's algorithm. It'll either be based on it or some kind of modification. And another application is something that I know we've all just recently experienced with LinkedIn. We can think about the connections between LinkedIn as we're all parts of a graph, and then all of our connections are other nodes. And then in order to find out the closest distance I am from people that I'm not actually connected to would be going through everyone in my realm and then everyone in that realm and then figuring out the shortest path between those two. And if y'all would like to look at more topics about just graphs and graphing algorithms, there's modified Dijkstra's algorithms, which will actually solve the other 2 categories of shortest paths that I just mentioned. And then Floyd-Warshall will solve the very last one. So that's all pairs shortest path. And then minimum spanning trees are also really interesting. It's part of graph theory, but if y'all are interested in this topic, these are further things you can look into. Thank you.